Alright, this smiley face is going to represent the planet Earth. Yay! Because it's a happy place, isn't it? Huh? Alright, I want you to remember another one item to remember is just a very subtle difference between two words, a rotation and a revolution. Rotations occur from within. The Earth rotates on its own internal axis, and that's what gives us night and day. Alright, okay. The Earth revolves around the Sun. The Sun is an external axis to rotate around, so that's called a revolution. Alright, that's the difference. A rotation is an internal axis. A revolution is an external axis that you're going in circles around. Cool? Alright. So, if I were to represent night and day with this smiley face, I would just have to do one of these, and for this demonstration, it doesn't matter where the sun is, who cares? Cool? And what you can obviously tell is this is on a turntable, and I put a calculator on the turntable. Now, this calculator I chose because calculators have two sides, a button side and a screen side. So there's buttons and there's screens. And what I'm going to do is arrange it so that the buttons are facing towards the center of the circle. This I will use to represent the moon. This I will use to represent your happy place, planet Earth. Oh, and what you guys all know is the moon always has the same side of it facing the planet Earth. Many people don't know what the physics behind that is, which is what I will explain to you a little bit about here. And then we will answer the question, does the moon in fact rotate around an internal axis in order to maintain it always facing in the same direction. Okay? So if I were to do one of these, what I want you to realize is that just simulated 28 days, ish, 28 days to have the moon go from this location in its orbital revolution around the sun, around the Earth, to that location again. A lunar cycle's ish 28 days, okay? So, me just doing one of these, and what you guys, again, all already know, those keys are always facing towards the Earth. A more accurate thing to do would be to have me have this guy go in 28 circles while this thing is rotating, but this sucker would have to go nuts going in circles. And I just don't have a motor or whatever capable of making this thing go in 28 circles for every one of those. So, we can kind of disregard the rotation of the Earth for this particular example, just, unless we're going to focus on what the moon is doing. Right? Now, another thing to remind yourself is hold on, sorry. Ooh, gosh, we get to hold our attendance today. I'll be darned. Okay. So, if, what you already know, the Earth is exerting a gravitational force on the moon. That's why it's still here after all these billions of some odd years. So, the Earth is pulling on the moon. Now, something else that you probably remember but haven't thought of in a while is when you are very close to something, that great gravitational force is strong, isn't it? Yeah. And as you get farther and farther and farther away, that force gets weaker, doesn't it? Gravity gets weaker with distance. So near is strong and far is weak. Okay? You guys know that, just to remind you. So, okay, a gravitational force gets weaker with distance. So if the Earth is tugging on the moon, it's tugging with a greater force on the near side of the moon and with a lesser force on the far side of the moon, okay? Provided the moon is big enough for that distance to produce a noticeable difference in that force, all right? So it's got to be a really big object for the force to change as you go across something. And what I will do is just use these guys to represent the difference in force. So some of you know what about, you know that hey, just your physics grade, that's a big F. The close side of the Earth, the moon, experiences a large force. Others of your physics grades are just a little F. That's not bad, huh? I'll put it way out there. The far side of the moon is experiencing a force, but it is a smaller one than the near side. Okay? So I'm just making a representation. Big F, big force, little f, little force, even though it's from the same planet Earth. It's this gravitational force radiating out in space, and that force gets weaker the farther away you go. So if a single object like this calculator, which represents the moon, if that moon is big enough, then it will experience a change in force across its body. All right, and that's called a tidal force, a delta F, a change in force across the body of an object. So what that means is, if the moon were to try to rotate and do one of these, to start rotating, can you tell the planet Earth will tug harder on this F than that F, and so it will pull it back down or back closer to itself. So if this big F tries to get farther away from the planet Earth will snap it back into place, pull it back like this. Or if it tried to go the other way, the planet Earth will pull that big F back towards itself. So if the moon tried to do one of these, the Earth will say, get that big F back towards the Earth. Okay? Or if it tried to go that direction, it will just pull it back towards itself. So what I want you to then realize is that larger F is what keeps that keys side of the calculator facing the happy place. All right? And again, if it tried to move a little, that force would pull it back and keep it facing itself. Okay? That's pretty easy to visualize once you have the two F's there. If it tried to rotate, it's going to pull it back in. Okay? The joke I tell, it's like The Godfather. It keeps pulling you back in. So, all right. Now, the other thing I'm going to say is, so in a 28-day lunar cycle, we keep going around. That force is still stronger here and weaker there, so it keeps that side towards it as we're going around one 28-day cycle. Now, what I'm going to ask you is, during that 28-day cycle, did the calculator rotate around an internal axis? Say, I don't know, that cosine button right there seems to be smack in the middle of it. Is the moon doing something like that, rotating around the cos button? And that's what we're going to just have to ask ourselves a little bit here. What if I ask you, what direction in the classroom now are these keys pointing towards? And I know you can't tell, but that way is the front of the classroom. Cool? And that way then is the back of the classroom. All right? And so what I want you to then think about is, if this is the start of our 28-day lunar cycle, then if there's 28, then 7-ish days later, 1/4 of 28, we're right here. 14 days later, half of 28, we're in half of a circle. And then 21 days later, 3/4, 28, we're kind of right there. And then in 28 days, we're right back where we started. Okay, so each 90-degree section of this is ish a week. All right, so let's come back a week later. These calculator buttons are facing the front of the room. A week later, are those calculator buttons facing the front of the room? And that answer is no. It's obviously pointing towards the side room. That's where the door is. That's my entrance room. If I come back a week after that, which is 2 weeks from where we started, now these keys are pointing towards the back of the room, aren't they? They're pointing in the opposite direction, aren't they? 14 days ago, those keys were pointing towards the front of the room. Now, those keys are pointing towards the back of the room. Well, how do you go from facing the front of the room to the back of the room? You rotate, don't you? If you're facing opposite directions, that's the definition of a rotation, isn't it? And then I wait another 14 days and I'm facing the front of the room again. So what if I want to get these keys to face the back of the room without turning the turntable? Well, then I would have to rotate it, wouldn't I? That's the exact same thing. Now the keys are pointing towards the back of the room. Now they're pointing towards the front of the room. I can get those keys to change what direction in the classroom they're pointing by simply doing this. That is an internal rotation, isn't it? So, as the moon is revolving around the Earth, it is also rotating around its own internal axis because the keys go from facing the front of the room to the back of the room, which is the same thing as simply rotating, right? It just is. Now, what if, one last thing, what if, while that moon is going in its circle, I want those keys to not rotate, meaning I want these keys to always face the front of the classroom, always face the front of the classroom for that entire 28-day cycle. Okay, let's envision that. Let's pretend in our headsies. So if I'm starting here, then 7 days later, shoot, they're not facing that way anymore. If I want them to continue facing that way, I have to rotate it, don't I? And now the keys are still facing the front of the room, right? So let's come back a week later, and if I want those keys to continue to face that way, I have to rotate the calculator, don't I? Now this is not what happens. I'm just showing you what would happen if it did. Now, if I want these keys to continue to face the front of the room, that's that way, I have to rotate it. So if I'm trying to prevent this calculator from rotating, meaning always have the keys facing the same direction, if I'm trying to prevent it from rotating, I have to rotate it. And if I want these keys to always point in the same direction towards the front of the room, then I have to rotate it, don't I? Okay? So I have no choice but to rotate it if I don't want it to rotate. Or it has no choice but to rotate as it's rotating. So whether it's whether it's rotating or not, it's rotating. What that means is the rate at which the moon does this, which is rotate on its internal axis, is exactly the same as the rate at which it rotates or revolves around the Earth, its external axis. Those are synchronized rotations and revolutions, okay? And so it's due to a tidal force, a stronger F here than there. What we say is the moon is tidally locked to the planet Earth, meaning it's always going to be locked to have this side face the same way. Now remember this, just from physics class, Newton's third law, whatever the Earth does to the moon does to the Earth. So give it a couple billion some odd years, and the Earth will always face the same side of the moon. So some folks will, at that point, they will be tidally locked with each other. So, anywho, whether it rotates or not, it's rotating.